Next, what I'd like to do is take a look at a problem in which the forces are applied in such a way that not all of them are perpendicular to the radius vector. So in other words, we're going to have to do that torque equals RF sine theta, where F sine theta is F perpendicular. That's the part of the force that is perpendicular to the radius vector. So here's our radius vector R, here's our force F, here's the F perpendicular part of it. And so that is a term that we will be looking at in this next problem. So this problem then involves a horizontal beam that's connected to a wall. So here's the wall. The rope is also connected to the wall and to the far side of the beam such that the angle between the rope and the beam is 30 degrees. And the beam is attached to the wall at this point here, point P. And so what we want to do then in this problem is to find the tension in the rope that will support this beam if a mass, M, that's equal to 100 kilograms is hanging from the edge of the beam, and the beam itself has a mass of 50 kilograms. Okay, so clearly we have forces that are acting here and torques. And so the first thing that I always recommend doing in a problem like this is to get a clearly labeled force diagram drawn. If you don't have the right force diagram, then everything else that you do from then on is going to be wrong. And so first we have to identify, well, what forces are acting on what? We've got the force of the beam acting on the wall. We've got the force of the rope acting on the wall. But that's not what we're interested in this problem. We're just interested in forces that act right on the beam. So those are the only forces we want to draw into our force diagram, because otherwise we're going to be confused by forces that don't matter. And so here, attached to the beam, we have a rope that exerts a tension T. Okay, so we can say that for sure. We can also say that there is a force acting on the beam from this hanging mass that's equal to big M times G. And we can go to the center of mass position of the beam, just like we did in the last problem, and pretend that all of the mass is located there. And that'll give us the right answer for the problem if we do that. And so we'll call this little m G, where little m, or mb, you call it here, is the mass of the beam, which is 50 kilograms. And then the entire length of this beam is 10 meters. So that's the length L here. And so is that it? No. There's also the forces of the wall acting on the beam. Now, how do we know that? Well, because the beam is pushing down because of its weight on the wall. So if we're made out of tissue paper, we would just tear it right out that way. And so therefore, there must be a reaction force of the wall on the beam that we'll call Ry. But also, if this were made out of tissue paper, the beam would impale itself right through the wall in this direction as well. And so that would be opposed by a reaction force Rx, which would be the force of the wall on the beam. Okay? And so here then we've got Ry, Rx, we've got little mg, big mg, and the tension. So the first thing that I would recommend is that we do our sum of forces equations, because those we're more used to. So we'll set the sum of the y forces equal to 0. Okay, but in order to do that, we have to break up the tension vector into x and y components. So this component would be Rf perpendicular, and so that would be equal to T sine 30. Whereas this component of the tension that acts inward toward the point of point P, where the beam is in contact with the wall, is going to be T cosine 30. Okay, so this will be the y component of the force, and then we've got these two y forces, and we've got Ry. So all of those have to be looked at here. We write this as Ry plus T sine 30 minus big M G minus the mass of the beam times G equals 0. Okay, so that's our y forces. Now we'll notice here we have one unknown, Ry, here, and another unknown here for the tension. So we have two unknowns in this equation. Means we can't solve yet for anything. But we can write the second equation, which is the sum of the x forces equals 0. So we'll go back over here. We'll see that we have Rx, that's a positive x force, and we have T cosine 30, that's a negative x force. So those have to add up to 0. Okay, remember this is an equilibrium problem. So these are the conditions for equilibrium. Still in chapter 13. So we have Rx minus T cosine 30 equals 0. Once again, we have Rx is an unknown, just as Ry was, and T is an unknown still here. So that means that between these two equations, we still can't solve for anything because it's two equations and three unknowns, Rx, Ry, and T. So you always want to be thinking that way. How many equations do I have? How many unknowns? So that means that we absolutely must use the torque equation. So how should we simplify then this figure? This figure indicates all of the forces that are acting, but we want to try to eliminate as many unknown forces as possible so that our torque equation also doesn't have all three unknowns in it. We don't want that because that would be an algebraic mess. And so what I'm going to do is I'm going to choose this point here as my pivot point. Notice that Ry and Rx intersect with that pivot point. And so that means there's no torque if I choose that pivot point produced by Ry and Rx. So that's the key to this, is to see that if the extension of your force vectors goes through that pivot point, then those unknown forces do not appear in your torque equation. And so that's our strategy here. So that was, remember, step 1 is be smart about how you choose your pivot point. Step 2 is to set up a table of clockwise torques and counterclockwise torques. And so once again, you can use your pencil to support something that might look like the beam from the edge like this. And so now I can apply little mg and big mg to the beam. That's going to make the system rotate clockwise about that chosen pivot point. So I'll put that in my torque clockwise column as mass of the beam times g times L over 2, where L will eventually plug in is 10 meters, if we need to. And then the other torque, because that's mg times L over 2, right? And so then now big G, or big M, is going to be L times big mg. So this is going to be big mg times L. And I'm just leaving it in terms of L here, so I don't have a lot of numbers. It turns out, in this problem, the L's are going to cancel anyway. Now finally, for the torque, the tension force is going to have to be broken up into a perpendicular component. That's F sine 30 times this total distance r. Okay? So that's the same thing then as F sine 30, in this case, times r. Okay, so that's your F perpendicular r, in this case, is T sine 30 times L, okay, because L is the length of our radius vector for the part of the tension that's perpendicular to the radius vector r. And so that will make the system want to rotate counterclockwise. So you want to always verify that you've got at least one in each column. Because if you don't, if they say all turn out to be clockwise, then the system's not in equilibrium. It's rotating. So that means you made a mistake if you have an equilibrium problem. So this is going to be t sine 30 times L. Okay, so now I've made my table of clockwise and counterclockwise torques. Now, all I have to do is set the sum of the clockwise torques equal to the sum of the counterclockwise torques. Okay, so the clockwise torques, you're going to have mass of the beam times G times L over 2 plus big M, mass of the hanging mass times G times L equals T sine 30 times L. Okay, now we're in business because this third equation is only got one unknown. I can cancel out the L's all the way through, and this gives us T times the sine of 30 is 1/2. Here we take this as 30, 60, 90, 1, 2, root 3. T sine of 30 is 1/2, so this is T times 1/2 equals, on the left, the mass of the beam, that's 50 kilograms, times G, 10 meters per second squared, times 1/2, because we've canceled out the L, plus 100 times G, which is 10, leaving out the units. And then solving this for the tension, T is going to be equal to 2 times this quantity here. It's going to be 2 times 50 times 10 is 500 divided by 2 is 250 plus, here we have 100 times 10 is 1,000. Okay, so that I just multiplied both sides of this equation through by 2, and then this becomes 500 divided by 2 is 250. This becomes 1,000 all multiplied by 2. So that's 1250 times 2, which is 2,500 newtons. Okay, so that sounds like an awful lot of newtons, 2,500. But remember here that it's the vertical component of the tension that supports this thing against the weight. Okay, and so since this is tipped at such an angle of 30 degrees, only half of the tension is oriented in the vertical position, and the other half is going to help to smash this beam into the wall, and it's going to have to be opposed by Rx. Okay, so that's step 1, is to get the torque, and from that to get the tension. Now I can go back into, let's say, this equation, because this only involves the tension in Rx. And so that means that I can solve that immediately for the x component of the reaction force, Rx. So if I do that, then this is going to be equation 2 here is going to be T cosine 30 equals Rx, but we have the tension, so that's 2,500 times root 3 over 2 equals Rx. And so that gives us 2,160. So So that means that the x component of the tension must have been pretty big, right? Well, t cosine 30, cosine of 30 is the square root of 3 over 2, so that's 86% of the tension. Okay, the tension was 2,500, so this is 86% of the tension. And that had to be opposed by an x component of the force that was equal. So that means that this wall has to withstand a lot of force, otherwise it's going to be punctured and you're going to impale that beam right through the wall. Now finally, we can use what we know about the tension to also solve for Ry in this top equation. In the top equation, we can write that Ry is equal to little m plus big M times g minus t sine of 30 degrees. Okay, so that's just this equation rewritten and solved for in terms of Ry. So that'll be equal to 50 plus 100 times g, 10, minus t, 2,500, times the sine of 30, which is 1/2. Okay, so that's going to be equal to here, this is 150 times 10 is 1,500 minus 1,250. Okay, 2,500 divided by 2 is 1,250. So that gives us a relatively modest value for Ry of 250 newtons. So now we've solved our three equations. This is equation 1, this is equation 2. Those are our conditions of equilibrium. And our third equation, which is the sum of the clockwise torques equals the sum of the counterclockwise torques, using the fact that torque is F times the sine of theta times our radius vector r to get our three unknowns.